either way. You can do the way Professor Sievers did yesterday, where you can do the points, you can write out the points and then shift all the points, or you can write the table. So I'm just showing you another option. If you're successful in doing it with the points, you don't need to do the table. Okay. All right, so I'm going to draw my table. Let me make it a little bit bigger. Okay, so what I write in the table is I write my X and then I write my parent function as my Y. So I write X here, and then for this problem, what's our parent function?
X squared.
X squared, yep. So I write X squared here. So I fill in my table with the parent function first. And of course, keep in mind that's Y, that's our Y. So typically our traditional 5 points that we like to use are the -2, -1, 0, 1, 2. These are great for X squareds. They're not so great for square roots. For square roots, we have other ones that we like to use. But for something like a line or a parabola or a cube, we do usually like to use these traditional choices, traditional points, where those are our X's, and then we plug them in and get our Y's. So what's -2 squared? What's our Y going to be?
Four.
4. Okay, and be careful, it's not -4. And then -1 squared.
1 squared. 1.
Okay, 0 squared.
0 squared,
Okay,
0.
good. Oh, I was hoping nobody would say 1, but it happens. 1 squared.
1 squared is
Wake
1.
up, wake up, everybody. Come
It's
on.
1.
1. Okay, 2 squared. Come on.
Squared is 4.
4. Okay, cool. So that's our parent function. So now what I do is I like to do the transformations on the table rather than the points. It's the same process. So we have 2 things going on in this problem. So what does the 1/4 represent? What's that doing?
Multiplying.
It's multiplying. Yeah, it's multiplying. But what does it do to our function? Does it like make it move left or right? Does it flip it over? Does it make it wider? Does it make it skinnier? Like what type of thing does the 1/4 do?
Making it larger.
So it makes it wider?
Yes.
Makes it wider? Okay.
Yeah.
So that means it's a vertical, what we call a vertical compression. Now you don't have to know those vocab necessarily, but this is vertically squishing it, right? It's like you're taking your shoe and you're stepping on it and it's squishing down a little bit. So instead of being a regular parabola like this, it's getting squished down a bit like that, like somebody squished it.
Yeah, it's fat, yes.
Yep, so it's vertical, if you want to know the word we use technically is vertical compression. But again, you can just think of vertically, I'm taking my boot and I'm stepping on it and squishing it down a little bit, okay? All right, so things that happen vertically, those affect the Y, right?
Mhm.
So we are going to multiply our Y by the 1/4. So if I come over to my table, I'm multiplying my Y's by 1/4. And I just do this all the way down on my table. Okay, so 4 times 1.
I'm sorry, is that 57? Or you just doing an example?
Oh no, this is the problem we went to groups to do. This is 55.
Oh, okay.
Did I write it
I thought
wrong?
you said 57.
Oh, no, 55. Did I
Oh.
type 57 in the chat on accident?
No, you said 54.
No, you're good.
Oh, okay.
I'm hearing things. I'm sorry. Oh, Jesus.
Okay. All right. So we're going to multiply by 1/4 all the way down. So multiply by 1/4 gives me 1. And you know, you don't have to write the work once you kind of know what you're doing. I'm just writing the work to show you so you know what's happening. Oh, whoops, I totally wrote the wrong number there. There we go. And then times 1/4 equals 1. Okay. All right. So I took care of the 1/4. That's done. That one's finished. So now what else is happening in this problem? What other shift or transformation is happening? We took care of that one.
You're adding 1 to it.
Adding 1. And what does that do to it? Does it go up, down, left, right, shrink, squish, stretch? What does it do?
To the left one unit.
Yep, it goes left. Okay, so when we think of left, left means we're subtracting with the y or with the x, right? If we're going left, we're subtracting. So I'm going to subtract by 1. So I'm going to subtract 1. Okay, on my table. So -2 minus 1 is -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. 2 minus 1 is 1. Okay. So now I have completed that transformation. So I'll put a little check mark. Are there any other transformations on this problem that we need to do?
We need to square it.
Squaring it is part of the parent function. So that we technically already have taken care of right here. Right, that's already taken care of. So is there anything else left on this function that we need to transform or move or do anything to? Or are we done? No one's responding. If you're not responding, does that mean you have questions? What are your questions then? Tell me something. Oops. Uh-oh, hang on. I'll share it again. My bad.
I wasn't fully understanding it at first, but I'm starting to get it more now. This is Charmaine.
Okay. I'm so sad that it just deleted all my work. Okay. Technology, yay. Okay, let me write my table again.
I don't know if you're having the issue, but my issue with it like closing was that my Bluetooth keyboard was interacting with it for some reason.
Mine was I accidentally clicked the not the stop share instead of undo. That was totally my fault. Yeah, so times 1/4. So this was 1, 1/4, 0, 1/4, and 1. And then this side we subtracted 1. So I'm just writing it again real quick since I lost it. Okay. So again, with that function we were talking about, was there anything else that we need to do?
I noticed they don't do any horizontal stretching or shrinking. They all do it all vertically. So I don't know if that's gonna
Oh,
help
okay.
them. But yeah, there's a relation between the two.
There is, yeah, they're inverse. Yeah. But anything else that we're doing for this problem? Or have we already completed all the moves?
I think
We
it's
need
complete.
just to draw them now.
Sorry, I couldn't hear what each of you were saying because you were talking at the same time.
I think it's complete.
Okay, yeah, it's complete, right? I was putting check marks as we went. I know my check marks got erased because I accidentally hit the wrong button. We did the quarter transformation. We did the +1 transformation, and there's nothing left. The x squared is our parent function. All right, so let's graph it now. So again, I'm going to use my table. And like I said, you can do it this way, or you can do it the way Professor Sievers was doing it yesterday. Both are fine. I'm just showing you another way. So I'm going to graph my points. So my first point is -3, 1. So -3, 1, 2, 3, 1, right there. That's my first point. Okay. Any questions on how I got that?
I did.
No?
No, you're a good teacher.
Okay. All right, next point, -2 1/4. So 1, 2 1/4. So it's gonna, whoop, that's a little bit higher than 1/4,
Small, this one is.
like there. All right, I'm gonna run out of colors here in a minute, but I'll try to keep switching. We're doing Christmas, I guess. If I had orange, I'd do Halloween. The next one is -1, 0. That's my next point. -1, 0 right there. Next point, 0, 1/4.
Is it
And
one? Yes.
the last point is 1,
1,
1.
1.
There we go. Now you should, when you do parabolas, it should be symmetric. So that means that both sides should kind of match from the vertex. You should be able to see that they look the same on each side. So that's a good way to check if you're having like a mistake happening. Okay, let me try to connect my little parabola here. Roughly like that. I know it's not perfect drawing it on the screen, but roughly like that. So again, it's entirely up to you if you want to use the table to keep it organized, or if you like points, you can do that as well. But you should get the same thing regardless.
Yes, I prefer to use the table like t-shirt. It's like, it's very accurate.
Yeah, I like the table just because I've usually done problems that are much harder than this, where there's like 6 transformations or 5 transformations, and I get really confused with all the points. So I just like a table because it keeps it organized, but it's preference. So either is fine. So how are we feeling about this? I want to see responses on your video. Thumbs up like, yeah, I'm good. Or like hands up, I got a question. Or like thumbs down, like I have no idea what's happening.
He did it.
Good.
Okay.
Here, 160.
Adele, I didn't see your response. Okay, you're good. Diana, I didn't see yours.
But here,
Sideways? Okay. Yeah.
excuse me, here our equation, it's our parabola, it's going to be left because the x is +1, right? It's going to be
Yes.
left with
Plus
minus
1.
0.
Moves
The
it left.
vertex is -0. Yeah. -1, 0.
All right, so I saw Jerry and Diana and Michael F. We're not totally sure. Do any of you have questions that I can help answer to help clarify it a little bit?
I'm just trying to remember the patterns, the processes, just repetition will help with that.
Yeah, I definitely do think that'll help. If you remember that website quizzes that I told everybody about, if you go there and you look up transformations there, you can use that as practice as well because it's multiple choice. So you get some something to look at and kind of see like, oh, is it this one or this one or this one? And then you keep practicing there and that'll help you remember it as well. Jerry, did you have a question? I know you said kind of like, eh.
I don't know how you got your x values, like the -2, -1, 0, 1, 2.
Yeah, so you can use any x values, but for a parabola, we typically use those traditional 5. I mean, technically you could use any, but those are like the nice, easy ones to use.
Oh, okay.
Parabola, yeah.
Okay.
And 0 is the vertex of the parent function of x squared. So having 0 in the middle is kind of nice because then you can see where your parabola gets moved to. You can see where the vertex gets moved to.
Okay, so like
Okay.
if I do 56, I could use the same x values for 56.
Yep, because that's another
Okay.
parabola. Mhm.
Okay. That's all. That's the only part I was confused at. The rest I understood.
Okay, cool. So I do want to apologize for having my ringer on. I have like an emergency call I'm waiting on. So I do apologize for if y'all have to hear my ringer. But that's the reason why it's on. So the only time you're not going to want to use those 5 points we talked about was square roots and cube roots. Those don't really do well with those 5 x's. Those we usually use other x's. But we can talk about that when we get to 59. But for parabolas and absolute values and lines and things like that, we can use those 5 x's. Those are like kind of traditional 5 x's to pick. Okay. All right, any other questions before we go try out number 56, which is very similar? No? Okay. All right, let's go back to groups and try 56.
0.
100.
100, uh-oh.
1,
0,
0.
4.
Yeah, so eventually once you do these enough times, you'll just be able to write these instantly because you're gonna have it memorized. You've squared it so many times. All right, so we have, looks like maybe 2 things going on here, right? 2 transformations happening. What's one of our transformations? Somebody tell me one of them.
Times it by 2.
So what does multiplying by 2 do? Does that go left, right, flip, squish, stretch? Like, what does it do? What does multiplying by 2 do?
Stretch.
Stretch, right? It's gonna make it go skinny, like you're sucking in your stomach, like getting taller and skinny. So that's what the 2 does. This is
He's
a
making diet.
yeah, the instant diet, suck in your stomach. I'm pretty sure I spelled that wrong. There we go. Okay, so vertical stretch, vertical. Woo. So vertical means y, right? Vertical is like a y transformation. So we're gonna multiply our y's by 2. Because that's what we're doing to get that vertical stretch. We're multiplying our y's by 2 and making it skinnier, taller.
Is silly putty still a thing?
Probably.
That's what it
I don't
reminds me of when you use silly putty with the comics and then you stretch it out.
Yep, there you go.
Oh, Professor Stevens, you I haven't heard. Oh, I'm sorry. I haven't heard about silly putty in a long. I'm older. I might be older than you, but it's been a while since I heard about silly putty and the little egg.
Yeah. Or any sort of goo, Play-Doh, squish, or goo, let it stretch out. Bleh. Yeah.
Flopper.
Yeah, it's still a thing.
Okay.
Is it gonna be on the right side of the graph? For sure.
Yeah, so because it's a vertical stretch, tell me which way is vertical. Are X is vertical or a Y is vertical? Which one is vertical?
Why?
Y. So that's why we're multiplying it on the Y side. We're doing it on the right because that's the Y side.
So how come it wasn't? How come it was not 2x squared instead of x
Because
squared?
parent function has no extra numbers at all. It's either x squared, y equals x, y equals square root of x, y equals absolute value of x. Like there's no extra numbers in it.
So-
It's just those parent function options.
Okay, so how did you get the 2?
So now we're going to our problem and we're saying, okay, what are some things that we're doing to it? Well, we're multiplying by 2. So multiplying by 2 does vertical stretch, like the silly putty.
No.
vertical stretch.
The multiplying the x squared times 2.
Mhm.
And I don't see that I don't see that as far as the equation goes, because I see a 16
Are you looking
and then
at
I
this-
multiply.
Are you looking
Huh?
at the problem? I don't see a 16 on this problem right here. I
So
see a
negative
2.
4 squared.
Well, I haven't squared anything yet. Wait, what? No, we already squared stuff. We took the x and we plugged it in. So we took the -2, we plugged it in and we got 2 squared, which is 4. So the squared we already did. We did that on our first step. So we did this right here. 2 squared is 4. So the squared is part of the parent function. That's before we do any transformations. So we took the -2, that's our x, and we plugged it in. We did -2 squared, and that gave us the 4 that's right here that I wrote there. So the squared we
No,
already
ma'am.
completed.
I'm trying to figure out how you like in the beginning of it, like how, because see, I understood number 55, how you got x squared times 1/4, because you took you squared everything, which is like 1 square is 1, and then you multiplied the 1/4
Yep,
with
that's what
the
we're gonna do.
1, right?
That's
But-
exactly what we're gonna do. We just haven't done it yet. Yeah, what you just said is exactly what we're working on right now. We're just doing
Okay.
it times 2 because it's a 2 this time instead of a 1/4. On the last problem, it was a 1/4. On this problem, it's a 2.
So 2 times -4 is 2.
Well, it's 2 times +4, and that'll be 8. So 2 times 4 is 8.
No, ma'am. I'm talking about how did you get the times 2 at the top? I haven't even started. I didn't even I haven't even looked at the points yet. I'm just trying to figure out how did you get the 2. So you went.
Right
So
here.
you did
Right here. Do
2
you see it? Do you see what I'm
times
saying?
-4 is 2. right?
No,
And
I did
then-
not get it from the table. I got it from the problem. Do you see where I'm putting the red arrow?
Right. You
Yeah,
did
that's
2
where I got the 2.
times -4 is 2, right?
But 2 times 4 is 8. So I'm not sure where you're getting. the
Oh,
2 times
okay.
-4. We're just doing that 2 right now. We have not touched this. We're not doing that yet. We are just doing the 2. We are
Oh,
only,
okay. I didn't know that you could do that.
yeah, like on the last problem, we only did the 1/4 on the right.
Huh.
Yeah.
I wasn't, okay. I didn't know that you could do that. Oh, okay.
Yeah, so we're doing one piece at a time. That's why I'm trying to break it down, one piece at a time. So right now we're multiplying by the 2. So 4 times 2, I already said, is 8. Tell me what the rest of the table is going to be on the right. All those
1
thumbs up,
times
people.
2 is 2. 0 times 0 is 0. 1 times 2 is 2. And 4 times 2 is 8.
Yep, okay, good. All those thumbs up, people, can help out. Okay, so we have completed the multiplication of the 2. So I'm going to put a little green check mark over there. We're done with that. That's been completed. So what is the other transformation that is left that we still have to do?
-4,
Uh-huh.
or to subtract 4.
Okay, and what does that do to our graph? Up, down, left, right?
Move it, it'll move it over 4.
Which way? You said over 4, which way?
To the right.
To the right, good. So the -4 moves it right 4. So if we're going right, is that an X transformation or a Y transformation? Are we moving X's or Y's if we're going to the right?
Yes, teacher.
The X, right?
Yes.
So we're moving to the right 4. That's adding
With 4
4 to
units.
the X. So add 4 to the X, right 4. So if you think about our graph, if we go right 4, that's 1, 2, 3, 4. So that's adding 4 plus 4. So let's do that to the right side of our table. Or left side, I'm sorry, I misspoke, left side. So -2, add 4.
It's 2.
2. Okay, all thumbs up, people. Thumbs up, people, share. What'd you get? Tell me.
I had subtracted, so, but
Oh,
the second
okay.
one would be,
Yeah, I have subtracted
it'd
2.
be
Would be
3.
Good.
Four.
Okay, wait.
4.
I'm really
5,
confused now.
6,
5,
and 6.
6. Yeah.
Okay, so the inside is always the confusing one. So I have a student that I've worked with before who always says the inside lies. So they're like, the inside is lying to me. If it says -4, I'm supposed to add 4. It's so confusing. It's always lying to me because that's just how the transformations are working when we memorize those transformations. If it says x -4 inside the parentheses from yesterday's lesson, you know that that's right 4. Right 4 is adding 4 to the x. If I have my x as a 1 and I move right 4, that makes it a 5. So the inside is always the opposite of what you think. That inside is tricky. So like I said, one of my students remembers it because they say, oh, that's right. The inside lies. It's lying to me every time. So if that helps you remember it. So the inside's always opposite of what you think. If it's subtracting, it means you got to add. If it's adding, it means you got to subtract. Just the inside.
Okay, yeah, I'm kind of confused on like how you find the X's themselves. Like how do you pick those out?
So those 5
That's what I'm
points,
having trouble
you're
with.
talking about the -2, -1, 0, 1, 2.
Yeah, like -2 and 4, and then -1 and 2. How are you finding those? Like, how do you set that up in the chart?
So whenever you have a parent function that's a squared, Those are like our 5 traditional points. So our traditional points are -2, (4), because when you plug in -2 squared, it's 4. -1, (1). Again, when you plug in the -1 squared, it's 1. Those are just our traditional 5 starting points.
Right, but why are they that way? Like, why do we pick those numbers?
Because there's the vertex in the middle and 2 on the left and 2 on the right. And they're the easy numbers. I mean, I could pick a -50 if you want. We could switch to -50, or we could do like 4/5. Who wants to do fractions? Should we pick x's with fractions?
I have never been a fan of fractions in any shape. Decimals always make so much more sense, like 99% of the time.
So technically, Charmaine, you could pick any x's you want, but these are the 5 that are like the easiest, that get 2 on the left, 2 on the right, and the vertex in the middle. So that's why we choose to use these 5 points.
I'm sorry, I don't get that. Is there another way to do that? Do this equation without doing a easier way? Because I'm very confused about how you would add 4.
We have to add 4
Because you're working on the inside. You're working on the inside first, but you put an x squared and then you started working on the 4.
The x squared is from the parent function. So the x squared, you got to memorize your parent functions. That's probably where it's coming from. You got to know the parent functions first. Parent is where we start. Then we move it around to get the child, the child function. Parent is always where we start. So again, there's a bunch of parent functions. There's y equals x squared, y equals absolute value of x, y equals square root of x. There's more than that even. But those are the 3 that they're having you work with on this page that we're doing. There's actually a lot more than that. There's like tons. But those are the 3 parent functions they're having you start with and that were in yesterday's notes.
Okay, but if I was to, I mean, I understand that the parent function was y equals x squared, but in order for me to be successful in making a graph, when you it's like you switched everything up. It's like you did, instead of doing everything in like x squared minus 16 and then adding or multiplying the 2 to it, and then finding the y square, you kind of broke it up in 2 different parts, and it's making me confused because I don't really understand where you were going with that. I mean, I think that, I mean, like,
well, that's why I said
I don't understand where the add the 4 was. Yeah,
well, so if you want to do it the way Professor Sievers did it yesterday, you can graph the parent function. If you want to do that, that's fine.
But you have to solve the internal part of it inside the brackets first, right? And then multiply by 2, then find the y value.
So if you don't like the table, that's fine. You can do the parent function Professor Sievers was doing yesterday. See, this is the parent function. I don't know if you can see it. It's kind of hard to see.
I see it.
That's the parent function. So this point right here, this point is -2, 4. So if you want to do it point by point and move 1 point at a time, you can do that, like Professor Sievers was doing yesterday. So you can take that point and you can say, okay, I am doing a vertical stretch of 2. I am multiplying my y by 2. So now that point looks like that, because I'm multiplying my y by 2. Then you can say, okay, now I'm going to the right 4, because that -4 is inside, subtracting 4 is inside, I'm going to the right 4. So that moves my point right 4, which makes this a 2, 8. And then you can graph that point, wherever it is, you can graph that point. You can do it 1 point at a time if the table is confusing to you. Like,
okay, so well, I mean, with the way that you're doing it, is it making the points, is it going the same way? I mean, will the points they'll be the same way, but what's the difference?
The difference is it's organized in a table versus just points written on the side. Because if I do it this way, I'm gonna get all these points written on the side, like a whole bunch of points that I have to write on the side, and it takes up a lot of space. I'm doing it in a table, so it's just staying organized all in one place. But it's up to you. I said at the beginning of the lesson today, you're welcome to do the points if that makes more sense to you. It's just for me, that's a lot more work to write out all the parentheses and keep it organized.
Okay, yeah, well, I understand that, but my confusion was, how were you solving the equation first? The equation is my problem with trying to get, was trying to figure out where do I start as far as finding the Y value of it.
You start with your parent function and then you look at your transformations. So that was from yesterday's lesson. So if you're struggling with that,
Okay.
you might want to review the transformations.
Okay, that's not what
That might help a little bit. Oh, well, I'm not sure what else. I'm not sure which part. You start with the parent function and then you move it. Oh, sound like you're taking a phone call. Okay. All right, let's continue then. So let's graph the points. If you haven't already, let's graph them. So 1, 2, 3, 4, 5, 6, 7, 8. 3 is 1, 2, 3.
Your 3 is 2.
Yeah, oh, whoops, you're right. I counted up 3. 1, 2, right there. Okay, 4 is 0. So it's right there. See, look, this one's going to be a little skinnier.
Yes.
Because it got that vertical stretch, so it's a little skinnier than the last one was actually flatter, like we'd stepped on it.
Because the last one is 1/4, and now is the leading way is 2.
Yep. So again, I just graphed these points. So 2, 8 I graphed, 3, 2 I graphed, 4, 0 I graphed, 5, 2 I graphed, and 6, 8 I graphed.
Yep.
Okay. Is there anyone out there that's liking the table, that prefers the table?
I do it in my way with tables.
Okay. Yeah. So I see Jonathan likes the table and wants to use it. Is anyone else liking the table?
I like the tables too.
Okay. Kathleen?
I like the table.
Okay. So a little.
Seems more straight to the point, more organized, less.
I like the way
fluff.
I like the way how Professor Sievers did it too, but the table like broke it down a lot more for me, so it made me understand what was going on more.
Okay. All right. I just wanted to get a feel, because if every single person said I don't like the table, then I would stop doing the table. But if we got a mix, then I'll do the table, and then y'all can rewatch yesterday's lesson if you like the points more as well. So you have both options. All right, cool. So let's go to the next problem. We've graphed it. We're good. The next problem, what's the parent function before I send you out? What's the parent function on the next one? Is it an x squared again?
Y equals square root of x.
Ooh, square root. So it's this one. So for your initial 5 points on this one, let's think about this before we go back to our group, so we can have a good starting 5 points here. Here's my x, here's my square root of x, which is my y. What happens if I start with -2? What happens if I take the square root of -2?
No, there's nothing.
It's undefined, right?
Yeah.
There's no solution to that. So those 5 key nice starting points don't really work so well with square root of x. So usually we pick some other 5 points traditionally. Traditionally we start with 0, because square root of 0 is a nice one. Then we do 1. What's another next nice number? Like square root of 2, is that going to give me a nice easy y, or is that going to give me a decimal?
Did you have a question, please? We are doing 59, right?
Yeah, the next problem, if that's the next one. I'd have to look, but I'm on the wrong screen.
For our 59, our f of x equals to 2 root minus x.
Yeah, I'm talking about the parent function. The parent function is y equals square root of x. Yeah. So I'm just getting the table started for those people who prefer the table.
Okay.
So I would start with a 0 anytime I do square root of x. Then I would go to a 1 anytime I do square root of x. What about a 2? Is 2 nice?
Should we
No.
just do odd numbers?
Yeah,
So like
2's not
0,
very
1,
nice.
3.
Well, what about 3? Does square root of 3, is that one nice?
No. 4.
What's the next nice one? Oh, 4. That's a nice one.
4.
And what's the next nice one?
9.
Yeah, I'd probably stop at 9. So that's probably a good way to start, okay? So for those of you who like the table, that's how I would start. I'll send you
So
back.
that
to-
negative sign doesn't matter in the square root?
This is the parent function. Start with the parent function and then we'll, yeah, but negative, you can't take a square root of a negative. Square root of negative is undefined. Yeah, that's why we didn't do a negative. Is vertical Y or is vertical X?
Vertical is Y.
Y. So Y is the second one, right? See the Y
Yes.
here?
Yes.
Yeah, so that
That's
means
what that's what Ganya said. Yes.
that's why we're going to multiply the second part by 2. Because it's a vertical and vertical is Y.
Okay.
So we're multiplying all of these by 2. Okay. So go through and multiply them all by 2. I think we get 0. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. So try to think about it. Am I going up, down? Is it vertical? If it's vertical, then I need to do the Y. Okay. All right. Any questions on the multiplying by 2 part? All right. Tell me, so I'll put a check mark there. What's the other transformation on this problem?
A negative.
Negative. What does the
Negative
negative
one.
do on the inside?
Across the y-axis.
Yeah, it flips your x's across, right? It flips them over. So it takes all your x's and it flips them over to the other side. Wherever they're at, it flips them
So it just changes the sign.
on all your x's. So our x's are going to be multiplied by a -1, right? That's how we are flipping our x's over. We're flipping them over the y-axis, but we are flipping the x's. So we are going to multiply by -1 because our x's are what is changing here. We are flipping our x's over. So we multiply our x's by -1. So here I'll put flipping x's over the y-axis. We also call it a reflection. Reflection. That's the technical term. All right. So 0 times -1. 0, 0 times, or I'm sorry,
Then the next
1
one
times
will be
-1.
1.
Uh-huh.
Yeah, -1.
-4.
Yep.
And -9.
There you go. Done. Graph it. Good to go. So we're just going to throw our points on the graph now. So 0, 0, right there. That's my first one, 0, 0. My second one is -1, 2.
Mhm.
My third one is -4, 4.
Here, teacher, I choose -2. I find 2.83 because I just choose 0, -1, -2. But it's okay. Yeah, no
Yeah,
problem.
you'll get the same picture.
Yes, we
You have
get this.
decimals. You just have
Yeah.
decimals you have to deal with. That's the difference.
Yeah.
And then -9, 6. So I think -9 is over here. 1, 2, 3, 4, 5, 6. There we go. Cool. So we connect them. Make it look kind of curvy, like our parent function.
It's going to be a language, yes.
And that's it. Okay. Any questions?
Your curve is so thin.
I know.
I
Any
need to zoom in it. Yes, it's okay.
For all the people that had their thumbs sideways, do you feel better about it now? Is it a thumbs up now, or do you have a question?
Feel better about it.
Better.
I understand it now.
Vanessa, do you feel better about it? I didn't see if you felt better about it. Vanessa? Vanessa? Okay, I guess Vanessa can't hear. All right, everyone else feels better about it though? Yeah. Okay, so the last problem is more of like a thinking problem. You can create a graph as an example if you'd like, or you could look at some of the graphs we've already kind of done in our notes or in our homework to do the last problem. So let me share back over to that one. Here we go. So the last problem here, did anyone do the last problem yet, by the way? No, okay.
From yesterday's work?
No, from today, we still have one more problem. We have number
Oh.
131.
Yep.
Okay, so it says if we have a graph, which is y equals f of x, and it gets a vertical stretch. So it's going skinny, right? Tall and skinny, holding your breath, stand on your toes. Tall and skinny, or a shrink, we step on it with our boot to become a new graph, which is g of x. Do the graphs have the same x-intercepts? What do we think? Will they have the same x-intercepts? If I make it skinny or I step on it and make it fatter, is it going to have the same x-intercepts?
No.
No? Okay. Can you explain your answer?
Well, because let's see. You have f of x and then g of x, so they'd be different. I don't think they would touch each other. I don't think so.
Maybe if we have like let's just make up something. Let's say like, okay, here's my graph. Like I'll just make up a picture. I didn't get that from anywhere. I'm just making it up. So these are my x-intercepts, right? Whatever these numbers are. Those are my x-intercepts. Now, if I make it skinnier, are the x-intercepts going to be the same?
No.
No, they won't be. So it'll be like skinnier like this, right? The x-intercepts are going to change. They're going to be closer to the y-axis. Or if I step on it with my boot and make it wider, then it's going to be out wider.
Right, so they wouldn't be the same then, right?
Exactly, it wouldn't be the same. Now, when is the only time that it would be the same? There's one occasion where it would be the same x-intercepts. One type of occasion.
If they started at 0?
Yeah, or if we just started on anywhere on the x-axis, right? Like what if my graph was here? This is my x-intercept. Well, if I make it skinnier, that's still my x-intercept because it's the vertex, right? If I make it wider, if I step on it, it's still going to have that vertex there. So the only time it should remain exactly the same x-intercepts is if the vertex is on the x-axis. Because then if it gets skinnier, it's still going to be there, or if it gets wider, it's still going to be there. So that's the time when it would remain the same. But other than that, it would always be different.
The
You said it would
x-intercepts?
remain the same, or
The
the x-axis would, or the x-intercept, sorry, would remain the same if it was on the what? What was the term you used?
If the x-intercept was the same as our vertex.
Thank you, vertex.
Yeah.
You mean, teacher, when if my vertex is 0, 0 and my x-intercept is 0, 0.
Well, it could be, it doesn't have to be 0, 0, but 0, 0 would work as well.
Yes, it's just an example.
Yeah, So let's say it was like -5 and I'm multiplying all my y's by 2. That's not going to change that because that point is -5, 0, right? So if I multiply my y by 2, wouldn't it still be 0?
Mm-hmm.
Yeah, so any vertex, if the vertex is your x-intercept, it wouldn't change when you just shrink it. Or,
Yeah, of course.
Are
Yeah,
you
yeah,
doing horizontal or vertical stretching and shrinking?
well, you said that they're only doing vertical and it says
If
vertical.
they do vertical, the x-intercepts will always stay the same
Why would they stay the same?
because it's still going to be the same factors with just a different coefficient out in front, basically. You're stretching.
Oh, I'm doing it
thing-
horizontally.
Yeah, I think you're doing horizontal
I'm doing horizontal.
stretch. If you're doing vertical stretch, your X coordinates will always stay the same because you're multiplying that Y
by zero.
by
yeah,
a number and
zero.
you're multiplying it by a 0. So
Yeah,
this
yeah, yeah.
closer and further away from the axis when you stretch it, but the things on the axis stay on the axis. That's like
Yeah.
the point that you're stretching about. You're pulling
Yeah.
it equally fast from both direction. And that's the axis is like your center, sort of.
Okay, so yeah, I was thinking of horizontal. Sorry, y'all. Erase that.
No, it's okay. You mean
So-
when it's vertical, your axis is going to be the same.
When, yeah, your x-intercepts will be the same because we're so remember we did earlier, when we stretched it, we multiplied by 2, for example. We had that problem, we multiplied by 2.
Mhm.
So here, if I multiply my y's by 2, aren't they still gonna be 0?
Yes.
So
it's
they're
zero.
gonna stay the same. Or if I multiply them by a quarter, like we had on the first problem, if I multiply my y's by a quarter, those are gonna stay the same. I was thinking of a horizontal.
That is it's a weird question, if I'm being honest, but it makes you think.
Okay, I want to just understand, teachers, please. Well, you said if we have the the same x-intercept to stay the same, like vertical in the x-axis is going to stay the same. I don't know how can I say it.
Anytime you're having a vertical stretch or shrink, so shrinking it up or stepping on it, that means we're multiplying the y. So if our y is 0, then it would never change, right?
Yeah, if it's up, it goes.
Yes.
If it's down.
That's why.
down.
Yeah, so it will never change if it's a vertical stretch or compression or shrink.
But if it's horizontal,
Your
Then
Y,
it's the opposite.
your Y-intercepts when you stretch it up and down will change, though, right?
Yes, yeah, we haven't got to the y-intercepts yet, but those will change. Yeah.
Okay.
But the x shouldn't change because we're multiplying by the 0. Whenever we multiply by 0, it's staying 0.
Yeah.
I was thinking of, like you were saying, Ganya, the horizontal it would.
Yeah. Thank you.
So if I were to draw another one here, then let's say I wanted to draw one that's skinnier, maybe it would look more like I don't know, like that. Or if I wanted to draw one that's wider, maybe it would look more like that. Right? But it would still go through those 2 points because no matter what I multiply the zeros by, they're going to stay zeros.
Yes.
Does that make sense? Yeah, a little bit.
Yeah.
Okay. All right. Now we'll talk about the y-intercepts because that's the second part of the question. So I can draw another graph. So for our y-intercepts, let's say this was our first graph. I'll just make one up again. And and again, my x-intercepts can't change because they're 0. So when I multiply all my y's by stuff, they're not going to change. But this point here, let's say I'm making this up. Let's say this is 0, -5. If I do a stretch or a compression, stepping on it with my boot, it's going to multiply the y. So will that change? Is it going to stay a -5 or will it change?
Stay -5.
So if I multiply my whole thing like we did in example 2, if I multiply this by 2, it's going to stay the same?
No,
it would change.
It
it
would
change.
Or if I multiply by a quarter, like our first example, right? It'll change.
Of course, yeah.
So just keep that in mind. It does have to go through the same x-intercepts. Whoops, that's a bad graph. Let me try again. So it does have to go through the x-intercepts, but the y-intercept could change.
They didn't ask him about horizontal. Well, we don't do horizontal stretching.
Yeah, that's where my brain was thinking horizontal. Yeah, but we're not doing those.
But I think the book, my college algebra book, I think it asked them even like the same thing, horizontal. You get the same sort of property, vice versa. I think basically.
Yeah, you do.
I think we have this question in the graded problem.
Oh, well, then I just did it for you. Okay, so again, quizzes. Y'all, I have a feeling from based on some of the questions that I was hearing that some people do need practice. So you can go to quizzes, enter code. You don't have to make an account and you can type in transformations. I wanted to do this today, but we ran out of time. And you can just, oh, that's geometry. Don't do one with geometry. You could click transformations, algebra. Oh my gosh, okay. Algebra, and then you can just pick one. And this one says like which parent function matches the graph, and you could do practices there. Or you could do, you know, transforming. See how we have the transformations? What happens when you add 3? So if you want to do practice, this is a good place to practice, to start memorizing your parent functions and your transformations.
Desmos is also a good tool.
Yeah, Desmos is a really good tool, and it's a good exploration tool if you want to just mess around with it and see what happens. Okay. All right, so that is the end of class. So we gotta let y'all go. If you have any questions, we'll be back in a couple minutes. But otherwise, good luck with homework tonight, and we'll see you tomorrow.
Thank you. See you tomorrow.